All right, today we're basically playing detective. We're diving into one of the biggest scientific mysteries of the early 20th century. And this whole story, it kicks off with a really simple but kind of terrifying question about, well, everything.
I'm not kidding. Why doesn't it? I mean, think about it. Based on what the smartest people on the planet knew about 100 years ago, every single atom, the ones in you, in the air you're breathing, in every star in the sky, they all should have collapsed in like a fraction of a second. So what's the deal? What's holding everything together? Let's get into it.
So the story really gets going with this picture of the atom. It came from a guy named Ernest Rutherford, and honestly, it was a brilliant idea. You've got this dense positive nucleus right in the middle, and then these little negative electrons orbiting it, kind of like a tiny solar system. It made so much sense. It was neat, intuitive, but there was a huge problem. Actually, two fatal flaws. And this is really the core of the whole mystery, right? The trouble with Rutherford's otherwise great model. It seemed like the physics that worked perfectly for planets and stars, well, it just completely fell apart when you try to apply it to something as tiny as an atom. Okay, so check this out. Flaw number one is what we call the death spiral. See, according to the physics of the time, an electron zipping around in an orbit is an accelerating charge. And the rule said that any accelerating charge has to give off energy. If it's losing energy, it's losing speed, and, well, it should spiral right into the nucleus in less than a nanosecond. Poof, game over for the atom. Then there's the second problem, the energy mystery. Rutherford's model had no explanation for why electrons only seem to exist at very specific, predictable energy levels. It just didn't make sense.
So what do you do when your best, most elegant model predicts a reality that is just impossible? Well, if you're a scientist, you start looking for clues. The answer had to be hiding somewhere in the data they were collecting from experiments. And that big break really came from two key developments. First, they had to completely rethink what light and radiation even were. And second, they had to figure out how to decode these strange little messages that atoms were sending out. We call them atomic spectra. So for today, we're going to tackle that first, absolutely crucial step. What is light, really? Turns out, to solve the mystery of the atom, we first have to solve the mystery of light. Because light, you see, has this kind of a secret identity. And uncovering that secret, well, it was about to change the world of physics forever. You know, for centuries, scientists were arguing back and forth. Is light a stream of tiny particles, or is it a wave? By the 1800s, pretty much everyone agreed, okay, the evidence is overwhelming, it's gotta be a wave. Case closed, right? Nope. Because then, a physicist named James Clerk Maxwell came along and just dropped this bombshell. Light isn't just any wave. It's an electromagnetic wave. Okay, so what on earth does that even mean? Well, what Maxwell figured out is that when you take an electrically charged particle and make it accelerate, it creates these ripples in the electric and magnetic fields that are literally everywhere. And those ripples, that's electromagnetic radiation. The visible light we see is just one tiny, tiny piece of that. And let me tell you, these waves are pretty weird. Just picture one coming right at you. The electric part of the wave is going up and down. At the exact same time, the magnetic part is going left and right. They're totally in sync, but they're at right angles to each other. And they're both at a right angle to the direction the wave is actually moving. And here's the kicker. Unlike sound or a wave in water, they don't need anything to travel through. They can just go right through the empty vacuum of space. This discovery was a total game changer. It opened up a whole new way of looking at the universe. Because once you know light is a wave, you can start to learn its language. You can start to decode it. So it turns out that all the light we can see with our eyes, it's just this tiny, tiny sliver of a much bigger reality. We call it the electromagnetic spectrum, and it includes everything from the super long, low-energy radio waves all the way up to the incredibly short, high-energy X-rays and gamma rays. So, how do we tell all these different waves apart? Well, we can describe any of them with just two basic properties. The first is wavelength. That's just the distance from the top of one wave to the top of the next one. The second is frequency, which is how many of those wave peaks pass by a certain point every single second. Okay, now here is the really mind-blowing part. It doesn't matter if it's a radio wave that's as long as a building or a gamma ray that's smaller than a single atom. In a vacuum, every single one of these waves travels at the exact same speed.
And that is the universal speed limit, the speed of light. We're talking about 300 million meters per second. Just incredibly fast. And this all leads to a really simple but super powerful little equation. The speed of light, which we call c, is always equal to its frequency multiplied by its wavelength. What that means is, if you know one of those properties, you can always figure out the other. They're totally connected. A really long wavelength means a really low frequency, and a super short wavelength means a super high frequency. They're locked together. So, figuring this out, understanding light as this predictable, measurable wave, was the first huge piece of the puzzle. It gave physicists the tools they desperately needed to finally crack the case of the collapsing atom. And that's really the key takeaway here. If you want to understand the totally bizarre rules of the world inside the atom, you have to study how matter interacts with radiation. The answers weren't found by somehow looking inside the atom. No, they were found by studying the light that atoms either soaked up or gave off. Which, of course, leaves us with a huge and pretty tantalizing new question. Okay, great. Light is a wave. But how can a wave, something that's all spread out, be the reason that a tiny little particle, the electron, is locked into a stable orbit? How does that even work? Well, that is the next piece of the puzzle. And figuring that one out, that was going to take a whole new revolution in physics.